This is already quite a complex topology, especially with this Catmull-Clark subdivision. The polygons are a little stretched in one direction, as you can see. They are not exactly square, or this is in a mesh. This is called the aspect ratio of the polygons. Normally, the aspect ratio for a let's say homogeneous deformation should be 1 more or less, which mean width by height of this rectangle should be more or less the same. So aspect ratio larger than 1 or smaller than 1 tends to create this kind of irregular polygons like rectangles. Okay, it should be best to work with aspect ratio 1, which is what we were doing here in Rhino mesh or grasshopper mesh, because you see that these look more like square. But in this Blender mesh, things are a little bit odd if you think about it. One thing that we can do in order to come up with a more regular topology in this sense of the aspect ratio is, once again, well, actually, it depends on the resolution that we want to achieve. Actually, this with 2 subdivisions is quite high resolution. So let me decrease this one step. I like working with this Catmull-Clark because I like the way it smoothens up this kind of vertex, inner vertex, or this kind of turn that we have here. But nevertheless, remember that you can always switch to simple if you want. And what I'm going to do in order to have a more regular topology, in this case, I'm going to go into edit mode of this mesh. So you see I have access to the vertices. And what I need now is to add cuts in order to, for example, this elongated rectangle, I want to split them so I have more square-ish shapes. Okay? And so I use the Control R. Control R means loop cut. And with the wheel of the mouse, I can add as many cuts as I want. The objective here is to come up with like a more a higher density of polygons along this mesh. Initially, eventually, if you consider this, for example, you see that this edge here is actually splitting the whole polygon here into 2 halves. But this part, as there is a corner, is shorter than this one. And so eventually what we can do, we can take this vertex here, and by using the shortcut Shift V makes this vertex slide along one edge. So if I Shift V, all of this doesn't need to be extremely precise. The important thing is to come up with a more regular aspect for this separation line. I want this to stay more or less at half the length of this edge. See? And so this way I can create a more even distribution of vertices along this this mesh side. So you see that now we have more or less the same length in this column of polygons and in this one. So we can do this whenever we have this kind of situation. So here things are already working just fine. This is fine. This is fine, but this is not. You see, this is a very small gap here and a huge gap here. So I take this, bring it more or less to half the size of this edge, and then I adjust this line of vertices correspondingly. So just to have a quick adjustment of this topology. Okay, and as for the rest, everything looks perfectly fine. Okay. So you see that now we have more or less a more regular aspect ratio for these polygons, and always in edit mode we can Control R, for example, here. We can Control R here. We can Control R here. Control R. Control R. Control R here. I do say a couple of times because it's quite a large extension, and Control R here like once. So in the end, we start having a higher resolution version of the same mesh, but with a more regular aspect, and of course with the loop topology that we were looking for. And also, if we go back to Cutmore-Clark, you see that polygons are a little more regular. Okay. So if you want a more uniform behavior in the two directions, you better adjust the aspect ratio of these polygons. But nevertheless, you can always work with the mesh that I already sent you. I'm going to save this and select this thing here, File, Export, Wavefront OBJ, and this is going to be not the Grasshopper Blender Start Mesh. This is going to be the Blender to Grasshopper Start Mesh. So the opposite. Oh, by the way, when you export from Blender, just double check that, for example, here is Blender Grasshopper Start Mesh object, but just check this selection only, or else you are going to export whatever it's in the file, even if it's hidden. Okay, so just to know it, because as you are going to create a huge exportation and also very big files. And so here in Rhino, I'm going to also import, and I'm going to import, let's go in our folder 2020 and PFN, and this is the Blender Grasshopper Start Mesh. So I'm going to import this, and here it is. Okay, so the interoperability workflow between Blender and Grasshopper can also use standard import-export from the two software, so native commands. But we will be using in a while the Mesh Sync plugin in order to do this operation, because we need to export different things than the ones that we have exported right now. So if I want Kangaroo to work with this mesh, I can take another mesh container, set one mesh, which is this one right now, and I'm going to hide the imported mesh. And without running the simulation initially, so this must be set to false, I'm going to transfer all of these wires here from the actual mesh, which is this one, to this other one. So I'm going to Control Shift and drag these wires here to the new mesh container. Okay, something like this. The first thing that I want to check is the corners, okay? Because we need corners, even if we now have a smooth mesh, else we won't have enough anchor point. For example, if I leave things like this, I will miss anchor points in this area, and all of this part will just simply fly away due to the vertical load that we are applying. And also this corner is set free. So in this case, I will use a slider as we did initially between 0 and pi. And so increase this until we see the proper set of anchor points. No matter if we have a couple of anchor points here, it doesn't matter. The important thing is to have enough anchor points, which means at least one per vertex or per corner, okay, something like this. So that's pretty good right now. Everything is being converted into an elastic network. Each vertex of the mesh is receiving this load. The only thing that I want to double check is that now we are missing the inner point, because we are no longer working with this polygonal mesh here. It is also true that we can also take this original mesh and leave it exactly in the same place, you see, as where it was imported, because we didn't move the mesh neither here nor in Blender. And so when we import the high resolution Cutmore-Clark mesh, it will occupy the same spot in this area. And so the closest point will also find a vertex along the new mesh. But we must work with the new mesh. So actually, you see that this closest point is actually using the old version. And so we can also plug the new mesh to the mesh vertices, okay? So it's like nothing, as you can see. The points just shifted a little, but they are actually vertices belonging to the new mesh. Okay, so now everything is properly set, and we can see what happens if we hide this and we simply run the simulation. We should also see the mesh. Yeah, it's this one. It was simply hidden. Now you see that the deformation is occurring, of course, but you might notice, let me also hide the original mesh. Okay. The different topology that we are using is actually determining a different deformation for this object. So the topological editing that we did in Blender not only is useful if you want to create this kind of different loops flowing along the mesh, because eventually you want to distribute some kind of oriented geometry or oriented panels along these loops, as we did 2 days ago. But it also has some effect as regards the deformation, of course, because remember that the mesh topology is what generates the elastic property of this body. Okay, so this dome here is actually, well, I would say more interesting than the previous one, than the original one, because of this possibility to bend along these loops. You see, so it's pretty nice to have this kind of topology. Of course, we can tweak things a little, but also see what happens, for example, especially in this area. This depends on the fact that there are quite different lengths for these polygons. So we should eventually um, create a more regular topology. Okay, so if you have more square-ish polygons and all of them more or less with the same length for the edges, you will have a smoother deformation. Okay, there are also some actions or some goals in Kangaroo that allow creating or there is this for example smooth component or smooth goal that tends to smooth up a mesh. So if I reset the simulation and also use a smooth component, like trying to smooth this mesh as a new action, a new goal, and you also have a strength which is set to 1, but you can use something like, I don't know, strength 5.00. Let's say that smoothing is important to us. So let's also, I think this thing here is making things slower, run slower. So I would eventually deactivate all the last part of this definition. I'm only interested in the deformed mesh. So when we run the simulation now, we will have some smoothing occurring. And we should see that this mesh does no longer have that kind of creases appearing along the way. Okay, so you see that we get an extremely smooth result. Now, what's the problem with this? The problem is that the mesh topology itself doesn't compromise the structural behavior of this thing. So the catenary structure that we get is still a catenary structure. Okay, the difference in shape depends on the topology and on distribution of the elastic fibers. Okay, what is eventually compromising the stability of this catenary structure is the smooth component, because if I don't smooth or if I don't try to smooth this mesh, the result will exactly be a catenary curve. But if I tend to smooth this mesh up, well, in this case, I'm changing the shape of the original catenary shape. And so this might be unstable. So just keep in mind that the best thing is to obtain always a regular topology. Okay? But nevertheless, this is quite interesting as a first result. And now the thing is that I have this mesh here. Of course, we also have the shortest walk, but this is not so relevant. This is not what we want exactly, because it's basically a dumb result. Okay, let's see what we can do in terms of fibers once we have this object, because this object is way more interesting than the previous one. Well, first of all, let's see, for example, what this mesh sync plugin can do. So there are two groups. One is export, one is import. And now I already have the mesh here in Grasshopper, so I want to export it. Okay, and so I'm going to pass this mesh to the mesh object that I want to export. And I want a path, so I need to define a path. You see that it's a standard text. You see the A icon. So you can do this with a panel, or you can do this however you please. I'm going to go in our folder. So the path is going to be simply this one. So copy, grab a panel, and paste the content. So I'm going to copy to use this as a path. And export is just a Boolean value. Okay, so you see that this is an empty Boolean parameter. You can plug here a button if you want. The button is normally false when it is not clicked, and it gets true only when you click it once. So if I click this one now, this thing will be exported in this path. So let's click on this. Let's go inside our path, and let's see what happens here. If we already have a result, let me sort things by last edit. I think I missed a name for this file. So in the path, eventually, I will also have to add a name, or else it is going to use the upper directory. So let's see if in 2020 we already have something. Is this? You see, it is 23 August 1146. So it's this one. My bad. I should have given a name, so I'm going to get rid of this. Yes. Let's go inside our folder. So the path is okay, but we also need to give a name to this. Okay, so if I do this, or if I use this backslash, the plugin will understand that this is also a folder. Okay, and I want this to be named like today's date. This is going to be Grasshopper to Blender deformed mesh. Okay, so this is going to be the name. And push this button, and now let's go into our PFN, and these are the exported data. You see, so we have two TXT files. One contains the faces, which is this is the connection scheme. Remember what we said 2 days ago about creating meshes in Rhino and Grasshopper. Not only you need the vertices, which are these ones. This is the list of vertices, and this is actually the connection scheme. So if you take this list and connect vertex number 138 with 183, 511, and 447, you will get the first quad. Okay, so this is the data that we get from this mesh sync export. Let's go to Blender. Now, if we go to Blender, we can do something like this. We can, in object mode, we can shift a plane, which is this one. And if we go into these object data properties here, after tessellate settings, you will find mesh sync. See? Mesh sync is the correspondent in Blender of what we have done now in Grasshopper. So we want to import data. Okay? So let's go here in this folder. So let's browse to the file that we want to import. I'm already in the course folder, and what I want to import is the faces. Okay, so this is going to be the path, and I want to import mesh data. And here the plane converts into the deformed mesh coming from Kangaroo, or well, in general, from Grasshopper. And the thing is that this mesh has the same topology as the original one, but it went under the deformation derived from Kangaroo forces and goals and whatever. Okay, so for example, if you want to use this thing as we did 2 days ago, in order to tessellate it with some oriented module, you can already do this because you only need to go into edit mode, press the face selection, select one quad, go into UV, reset the UVs of this mesh, and then hit A, select all, and determine the UV following the active quad, which means basically understand what are the loops according to this active quad here. And that's it. The only thing that we need right now is the module. So I'm going to use a plane as we did 2 days ago. I'm going into edit mode, I'm adding a couple of, well, not a couple, but 3 loop cuts here. Switch to face selection, delete this with X faces. And now I have 2 faces. Select them, extrude them, and give them some thickness. That's it. This is our module. And then select the module, shift select the target mesh, go into the tissue, tab, decide to tessellate this, and simply hit OK. And now that we have the tessellated object, remember to go inside the tessellate settings. And as for the rotation, you want to follow the active UV. So this is going to orient the stripes along the topology and the UV coordinates of the mesh. And you can rotate them in order to have different orientation for these stripes. Okay. And also remember that this is a non-destructive workflow. So if I take the base mesh and apply, for example, some modifier, like I want to increase the resolution by creating a subdivision surface like this, then I can go back to the tessellation object, go into the tessellate settings, and say I want to use the modifiers for the base plane, which is actually the deformed mesh. So if I use modifier, you see that now I have a denser pattern of stripes. And to this thing, by the way, you can also add another modifier like subdivision surface in order to have more resolution. But in this case, if you do this, you will have separated modules. Let's see this in a while, you see, because our model is discontinuous. And so if you want to tweak things, you must go into edit mode, get rid of this face, this side face, the other side face, the other side, the other side. Delete all of these faces, and then select edges and mark this, and this, and also this one here. Mark them as seam. And now if we go here, you can also tell tissue or the tessellation that you want to merge the actual elements. So the seam get stitched together, and you have this smooth repetition of stripes. Okay, so if you want to see this in shaded mode, here it is. And how smooth they are, it depends on how much subdivisions you want to apply to this thing. Okay, so now they are 2, but I can increase it to 3, and you see that I smoothing this thing up. So pretty nice result, because we are working now with a very complex mesh coming from a double step workflow, which is adjusting the topology in Blender, creating the deformed object in Kangaroo, so it has some structural meaning already, and then applying this kind of tessellation, complex tessellation in Blender again through tissue. But this is not the point, actually. So this is another branch of our workflow. So if you want to work and create this kind of complex pattern on top of your surfaces, you can do this by using the tissue plugin by tessellating things. Okay. But the thing is that we want to create a truss system or something like that on top of the structural mesh that we obtained from Kangaroo, which is still this one. So actually, I don't need, or rather, if I apply some subdivision algorithm or subdivision modifier to this, I don't want to use the Catmull-Clark, because if I do this, you see that the corners are no longer touching the ground because they get smoothened by the algorithm. Okay, so eventually, I'm more interested in applying a simple subdivision, so I get a higher resolution. But this eventually, we will discuss this later on. You see that now if I do this, I am only adding more polygons, which are only visible in wireframe. Because as there is no smoothing, due to the fact that I'm not using a Catmull-Clark, as there is no smoothing, you see that basically it's like having a flat square and divide it by, I don't know, 4 by 4, but all the polygons lie on the same flat orientation of the original polygon. So even if you are increasing the resolution, you are not changing the shape of this object. It will be also like faceted like this. Okay, but in any case, I'm not going to add a modifier to this right now. I'm just sticking with the original thing. I will move this away because I want to concentrate on this deformed mesh. So this is going to be the Grasshopper Blender deformed. And what I want to do right now is a different thing. This is, by the way, the module that determined this kind of pattern. Okay. Let me also get rid, or well, hide at least the original mesh, imported mesh, the base mesh, and let's concentrate on this. Okay. Let's also hide the tessellation and the module. Okay, so this is what I want to concentrate on. So what I'm going to do right now, I'm going to add a module or a plane. Okay, and what I want to do is go in edit mode and select this face here and shift D, duplicate it along the Z direction. So hit the Z button and get to this thing here. And I want to go in vertex selection. So now what I want to do is create a module which is not three-dimensional, or it is not a solid module or some kind of surface. I just want to create lines. Why? Because remember that in Grasshopper, the shortest walk algorithm needs a line structure, or rather a truss structure made up of lines, so that the shortest walk can be calculated along these segments. So what if we provide something to Grasshopper made up only of lines? Okay, so what I'm going to do right now is something like this. I'm going also to select face, select the lower face, Shift D, Z, put it at some intermediate point between the two original faces and scale it like this. Okay, so I'm getting to this structure where I have three surfaces, three mesh polygons at a different height. Okay, so go back to vertex selection. What I'm going to do, I'm going to select this one, this vertex, with this vertex here, and hit F. F is creating a face between two vertices. So the only thing that it can create is actually an edge. So if I do the same here, so face, face, and face, and I also do this upward, like face here, face here, face here, and a face here on the other side. Now I have three polygons and a bunch of edges. I don't need the polygons, the faces. I only need the edges. So I go into face selection, select this, X, delete faces. You see that I no longer have the horizontal connection, right? So hit this, X, delete faces. Now if I delete this, I also miss the horizontal connection. This is something I don't want. Okay, so in this case, for example, I cannot avoid this because there is no option for deleting just this face. I must rebuild with vertex selection. I must rebuild these edges here with the same method. So I have created this structure here, which basically resembles a quad. It's a three-dimensional structure. I can make this thing as complex as I want. It's only made up of edges. And the moment that, for example, if you imagine that this will apply inside one polygon, like this, the moment you have the closest polygon here, you will have another, let's say, small square here at this height. So there will be this connection edge, this connection edge, this connection edge, and this one. So everything will become interconnected, you see? So you will get this kind of pattern that rises up or down according to the level that you want to consider. There are some horizontal connection, which is this small square here, and then it goes up again or down again. And then once again, up or down, square, up, down, square, and so on. So we are creating a, well, it's not a complex, let's say, a trust system, but it's an unusual, let's say so, trust system. Something that it's quite unlikely that you can get to this thing automatically. And remember that you can do whatever you please with these things. I mean, you can also, for example, decide that you want to connect diagonally here on top and with the opposite diagonal here at the bottom. You can do whatever you want with this thing. Okay. This, let's go back to object mode, is going to be our module. Okay. And so I select this, shift select target surface or the target mesh, and tessellate this and hit OK. So here's what you get. Now these are simple lines, okay? And it's a trust system. Now what I want is, for example, this flat square. You see that if you take a look at this mesh from this side, you see that this is the height of the flat square, because you recognize that there are the diagonals here. So the flat square lies on top of this mesh, but with some separation, okay? Let's go into the object data properties of this tessellation object. You will see that there is an offset here. An offset is 1 or -1. If I set this to 0, then the mid height of this module lies exactly on the mesh polygons. Okay, so I'm aligning these squares here on top of each polygon. You see that these squares lie on the center of each quad of the mesh. So now we have an interesting trust system with some aesthetic value as well, because we can decide what's the aesthetic of this structure, because we are designing it by hand, basically. Remember that tissue can also work with modifiers. So if I go back to the base mesh that we're using and I go into the modifier section and add some subdivision surface, for example, with or without Catmull-Clark, well, it doesn't matter at this point, but I prefer to do it simple right now because I want the anchor point to touch the ground. And if I go back and select the tessellation object and go into object data properties, I can refresh this by selecting use the modifiers. And you see that we get quite a denser set of line. Remember that the denser or the higher resolution the curve system for the shortest walk, the nicer result you will get in terms of fibers. Okay, so it's good to have this kind of control. And once we have this, remember that we are in Blender. Okay, so if I move this away, once we have this is another mesh object. It's just made up of edges. It has no faces, but it's a mesh object, right? So in object data properties, besides the tessellate settings, we also have the mesh sync. And as there is an import part, there is also an export part. And so I can decide, for example, where to put this the export file. I'm going to use the same path here, and I'm going to name this something like 200823. This is going to be GH Blender Grasshopper, and this is going to be the fibers base structure. Okay, something like this. Accept. And hit export mesh data. Let's go in our folder, and you will see that now we have new files. Let me expand this. We have new files. So Blender to Grasshopper is made up of 3 things. It is vertices, edges, and faces. Okay. Now, faces is actually 0 byte, as you can see, because our exported mesh had no faces. But vertices, it's 1.59 megabytes, and edges, it's 343 kilobytes. Okay, so the faces is actually an empty file. Now I want this thing to be imported inside Grasshopper. Okay, so let me save this file, by the way. Let's go back in our Grasshopper definition. So as we have the mesh sync export, there is also some import. Now, The only thing that I'm going to point out here is the mesh sync import and mesh sync import advanced. Now, if you use mesh sync import, you can just import a mesh. But if you want to import a mesh with its analytical features like vertices, edges, and so on, then you must use the import advanced. As our mesh is made up only of edges and vertices, you must use the mesh sync import advanced. Okay. Now, import is once again a Boolean value. So I can take this. Well, no, actually, I don't need to take this because I need a permanent import. So if I only push the button once, then the button will import the object. And then when I release the button, then this component will no longer import the object. So I need this to be permanently false or permanently true. Okay? And the path. The path in this case is going to be the actual path of these files here. So remember, always select the faces, even if it's empty. Select these. I'm going to go into properties and let's see if I can. No, this is only the actual path. So let's copy this. Let's create a panel with the actual path, and then also let's copy the file name, which by the way is a txt file. So let's go inside the panel backslash this name dot txt. So it should be enough to import this thing. This is going to be the path, and let's turn this to true. The amount of geometry that we are importing is quite a lot. The edges, actually, you see that there are 57,600 edges. Now, this is not exactly true. Now we are going to take a look at this. But you see that now we have this object here. You only see the vertices, actually, because edges, you see that it's a data tree with several branches with two values inside. Let's take a look at what we have here in order to understand what is happening. And you see that they are indices, 8 and 9, or 9 and 11, 10 and 11. Okay, so this thing here is actually importing only the vertices. Okay, what it's really doing is importing the vertices. We must come up with a set of lines in order to feed the curves input in the shortest walk component. So what I'm going to do right now is vertices are actually the points. So you see the coordinates, 28,800 points. Edges is the connection scheme of these points in order to obtain the edges. So what I need to do, I need to create a list item, extracting from this list of vertices, I want to extract these indices. So if I do this, I get a data tree with 2 elements per each branch, but now inside this branch, I will find a couple of points. Let's see. Here they are. It's quite heavy, this calculation, but here they are. So a couple of points, how do we connect them with a straight line with a polyline segment? So if I do this, finally, if we hide all the vertices, all these vertices, we get our structure made up only of lines. Okay. So I no longer need to see the result of kangaroo mesh. I have my base structure here of lines. Remember that this is only visible if as long as you keep this to true. Okay, so if I stop importing this, then everything here will become empty, of course. So this was actually the pattern according to our original square grid, basically. But now we have a different grid, which is these polylines, these lines here. You see that now we are getting a data tree, but that's why I put a flatten here. So we can plug this here. And you see that now things are starting to become a little more interesting. At least as for the shape of these flow lines, you see that you have a more interesting result. Okay, so this is the first step. Just confirm that everyone is okay with this before we move on, because just so that I know we are all in sync. there any problem? Okay, Sagar is good. Arish, are you good? All good, perfect. So I told you this is the first step, okay? Because we don't want this. This is not a fiber system, actually. You know, even if it's created by the shortest walk, this is absolutely, we are far from having a fiber system. You can clearly understand. So what I'm going to do, I'm going to use eventually these lines that we got here as the base of our fiber system. So let's consider as if these were some stress lines, okay? Um, the method that we are going to use is exactly the same that we used yesterday. So let's say we have this network of connections. So these are the lines, okay, that we want to follow as the shortest walk. So if I divide these curves, I get these sets of points. If I shift list these sets of points without wrapping, once I will use -1 in order to shift back the list of vertices. And a second time, I will be using a variable shifting between 0 and 5. Remember this thing that we did yesterday. As if you want the fibers to move away from the path, like perpendicularly, then you use a low number. If you want the path to align along the desired paths, then you increase this value. Also remember that the amount of points is quite important. So let's grab an 11 slider and decide if you want less or more subdivision. Okay, so let's work with a few subdivision, and let's leave this to 1 or 2, because with this separation, 1 and 2 means already moved forward along the path. Okay, and so we have these. We also need to work with the actual mesh vertices that are these ones in order to calculate the closest points. So closest point, I want to determine which are the closest points starting from these points here, considering this cloud of vertices. And so you see that there is some shifting occurring between the point, the original point, this divide curve or shift list, you see, and the closest point, which are this one. Okay, and let's repeat the same for this other set of points. Okay, so we have two different sets of points here. Let's double check what we have. We have a data tree with 5 points per line. And here we have a data tree with 4 points per line. So there is something, let's say, wrong with this, because we should have the same amount of points. So 20 branches with 5 points each. We have here 20 branches with 5 points, and here we have 20 branches with 4. Why is this happening? Oh, we have 6 initially. So let me see, because I think that, yeah, I think in this case, as we are working with several paths, we can no longer, let's say, increase this as we please. So we can also simplify this definition by simply putting 1. If you increase this value more and more, you are going to eliminate more values, because you are not wrapping the values of this list. So -1 plus 1 is the only thing that we can do at this point. So 5 here and 5 here. Remember that we want to generate hairs along these lines. So I'm going to use a point emitter from the end point of this. Just use a lower amount of points. Don't create this kind of huge point clouds, because that is going to be a mess in terms of time, of calculation time. And also the radius. The radius, you can leave this a little more close to the original point position. So something like, I don't know, something like this. You see that we are decreasing the distance between the point cloud and the actual point position. The important thing at this stage is that no matter what value you are forced to use, just use a value that creates some dispersion, but still allows to recognize what are the original paths, you see? because if you increase this too much, you get a cloud, a point cloud that simply, well, covers the whole shape. And this is confusing because the fibers are going to come up like randomly, okay? So as long as you still recognize the paths, then you can use this radius as a value. And so we now have these 5 points per branch, 20 branches, and now here we have 5 points per branch, but we no longer have 20 branches. You see the indices of this data tree is a little more complex than the data tree here. If you want, you can also see this visually with a param viewer. This is the actual data tree from the closest point, and also for this closest point here is absolutely the same. But if you take a look at the data tree coming out from this point emitter, it's a little bit more complex, okay? Because each of these branch is actually split into other because we have these point clouds for each point, okay? So we need the same structure here. We want to connect each of these points here with these 5 points coming from this point emitter. So if I graft this closest point, I now get this structure, just so that you see it. We get this, and we get this. So they are equal right now. And so now I can connect with a line, point A to point B. I can connect the start point to these endpoints here. And we start getting these hairs all along our paths. See? And these lines here are going to be our wanted path. Wanted path as lists. So once again, let's flatten this because this is going to create a data tree of lines, as you can see. And let's plug them here. Let's wait for a while. But in the end, if we hide the points, for example, we start getting this fiber system, which look a little more interesting. So remember that we are following this connection line, which we created with the non-incestuous network. But you see that the fibers originate from those lines and tend to spread away from them because of the hairs that we created here, okay? And also remember that what we did yesterday was, we can also scale these lines starting from the start point with a scale factor that is something like between 1 and, I don't know, 2, maybe. So, and use this lately as the wanted path. But if I do this, if I increase this, I'm extending these lines. And so the fibers can spread from the original line far from it, or stay close if this is set to 1. Okay, so if I set this to 2, for example, and use the scaled version of these lines as a wanted path, I will get larger fibers that tend to cover a wider portion of our structure. Okay, so you can see that this result is actually a little more interesting than the previous one. And as we are creating these hairs also tends to go up from the surface. And this is interesting because we are using a three-dimensional truss system. And so this line, these peaks that we have here, depends on the fact that some of these wanted paths are actually reaching a higher level with respect to the underlying mesh. And so we are taking advantage of this three-dimensional truss system. So these are not lines flowing along the mesh. Sometimes they separate from the mesh up or down from the mesh level. The shortest walk is actually emitting this kind of result, which are, in my case, 500 polylines. And so the next step, as you might recollect, is to actually convert these things into some solid shape. Yesterday we used Cocoon. Today I'm going to use Dendro. Okay, so I'm going to use the other alternative that we have, just so that you have another tool that you can use. Dendro is quite interesting, actually. It's faster than Cocoon, and it has, well, in my opinion, it has, well, not more potential, but a different potential with respect to Cocoon. So let's see how it works. So we have a bunch of shortest walk. We should also, they are 500, okay? So when I see this red thing here, it means that something went wrong. You see that it only says the start and end positions are equal. So this is something that already happened to us yesterday. Remember that when this happens, the command is probably generating a segment with 0 length. So basically a null object, okay? And we don't want to carry on with a null object along the path. So just to make sure that there is no null object, let's clean tree this thing. So we have 500 here, and we have 499. So you can see that in this case, there was no chance of visually detecting this null object because it's lost inside this list of 500 elements. So just for sure, make this adjustment here, double check that something went away, and then you're safe that the null object has been removed, okay? And so once we have this, we have the set of curves. Now, Dendro. Dendro can convert curve to volume, mesh to volume, or points to volume, okay? So it doesn't accept B reps. Remember that Cocoon has a B rep charge, which is basically a surface or polysurface to volume, okay? As for the rest, we have curves and point, just like in Dendro. So the main difference is that Dendro works with eventually mesh as three-dimensional objects, okay? We have curves because polylines are curves. Now, let's try the curve to volume. Let's plug this here. And it needs also other two inputs, the curve radius, which is something very similar to Cocoon. He wants to know what kind of thickness you want to give to these lines, okay? And there is also these settings. These two things work together. Curve radius and settings work together. So you might want to also grab create settings command here, because remember what I was saying yesterday, Cocoon and Dendro are based on marching cubes and voxel. You see that there is the voxel size here. So basically what this volume wants to know is what is the volume size and what's the size of the cubes you want to use to fill up this volume, okay? Now there is a particular condition here that says that voxel size must be at least, I don't remember, 1/3 of the actual curve radius, but we will discover this in a while. So just consider the size of the things that we are going to give thickness to. So we have these curves. This square is 1 by 1. So let's say we want to give a thickness of 0.25 to these lines here, okay? So I'm going to set a slider like 0.25, and I want to use this as a radius. But if I use the same value as a voxel size and plug this into settings, you see that nothing happens actually. And this says that radius must be at least 33% larger than voxel size, which is basically obvious. Because if we are determining, for example, with this radius, we are determining that if this is the line, and we want this to be the radius, which is 0.25, something like this, okay? We cannot use voxels, which are cubes, basically, with exactly this size. Because in this case, no voxel would fit inside this volume, or not enough voxels would fit inside this volume. So there is no possibility to create the volume, okay? So what I do normally, in order to have this problem solved automatically, is grab the voxel size input, right-click, create an expression, x divided by 1.33 should be enough. But as we are working with decimal values, like 0.25, we are not sure because some rounding should happen or could happen that would avoid the volume creation to succeed. And so I normally increase this to 1.4 or 1.5 just to make sure. And so you see that now the volume has been created. And you see that it's very, very fast, okay? So this is actually the volume coming out from this curves system. which, by the way, we can hide in order to have just a perception of what are the actual fibers along these paths. Of course, we could also, we skipped a step in this case. Remember that we can rebuild the actual curve that come out from the original shortest walk. And you see that this time, as we have a more interesting pattern or more interesting diagram, rebuilding has a totally different effect. So see how nice it is to have this kind of lines or pattern across this surface. Okay, so it's extremely pleasant design. And of course, everything depends on the degree. I will make these things organic. They were polylines, by the way. And let's grab an amount of control points like between 4 and 50. If I use 4, I smoothen these curves too much, as you can see. It's always nice as a design, if you think about it, but it's less relevant. And it also starts to cut through the mesh or just disconnect from the mesh too much because of the smoothing that is happening here. So if we tend to increase the amount of control points, we start to recover the original fiber system shape. Okay, so you see, the more points, the more zigzag you start to obtain, because this is what you get from the underlying truss structure. So just find a balance between these in order to have more or less the aspect, but not the details. Okay, and therefore you could also use these as curves. So the curves that I want to use are no longer the actual paths, but these ones. And this starts to be a little more interesting because you have a more smooth aspect for your curves. And Dendro is so fast because it is actually not generating any mesh. So the thing that you see here is not actually a real mesh. It is called a volume, Dendro volume, but this is the equivalent of the marching cube algorithm that we saw in Cocoon yesterday. Okay, it's like a preview of the final mesh that you are going to obtain. And if you want to convert this into a mesh, you must go into convert, volume to mesh, connect volume with volume, and this is also asking for volume settings, which are basically the same settings that we had here. And so now we have two objects, the volume, which is this one, and the volume to mesh. If I hide the volume, I now see the mesh with its edges. Okay, so if everything went right, I can right-click on mesh and bake it and hit OK. And so we have this object here, which is actually the fiber system applied to our kangaroo shape. Now, this is only, let's say, a dummy pattern, because this has no structural meaning, because these paths have nothing to do with stress lines. Okay, but you can use, for example, some structural analysis softwares. I'm going to quickly go through a very simple structural analysis on this. I could use Karamba 3D because I told you I have the licensed version, but as I think you don't, I will simply concentrate on Millipede. So I'm going to hide also this last part here, and I'm only going back to focus on the deformed mesh. Remember that this has some smoothing going on. Okay, so this is not actually a proper catenary structure, but when you perform some structural analysis, it doesn't matter what shape you are using, the structural software will always find a structural solution for this thing. Eventually, it will be not optimized because the shape is not exactly a catenary structure, but you will always come up with some results. By the way, I should have turned this off once it has converged. Turn this off once it converges, especially if you do some heavy calculation like this one after kangaroo, because if you, by the chance, change something here, this will update in real time this calculation, which will update in real time all the calculation that we have done so far. So it's going to be some heavy calculation and some time-consuming processes going on. So when you have the equilibrium status like converged, set this to false and avoid surprises. So I want to calculate things on this surface here. And what I'm going to do, I'm going to separate this workflow. So I'm going to take a mesh container and send this to this mesh here. Okay. So I'm going to create a different workflow. And let's go into the, well, where is it? Yeah, Millipede interface. I don't know if you know Millipede already. Have you ever worked with it? Nope. Okay. Used once. Okay. So basically, Millipede is a finite element analysis system. Um, so you can use it um, for structural analysis, basically, but also for topological optimization. I don't want to do a commercial right now, but if you have never used this, I do recommend that you have a look at least at let me see if I can quickly find it. Yeah, it's this one, the Grasshopper Architecture video course. It is actually already online, so if you purchase this course, you will already have access to the whole set of sessions. It should be 6 sessions. But here, for example, I think I'm opening this because there are some images, if I'm not wrong. Yeah, there are some images. So you can see that this is what you can do with Millipede and Caramba 3D. So you see deflection, stress, and this is Caramba 3D, by the way. The previous one was Millipede. This is topological optimization for a beam under precise, or this is a more complex structure, but always topological optimization. So everything is covered inside this course. So I do recommend that if you're interested in this kind of things, just give it a look because it's interesting. But nevertheless, what we are going to do right now is perform some structural analysis on this thing, but not because we want to come up with a real structural analysis, but only because I want some stress lines. Okay. So first of all, we must create the FE system. So we go here. And what we have is a mesh. So I'm going to create an FE mesh. I don't know if you're aware, but Millipede has expired. Well, definitely expired. So basically, it's discontinued. So even if you go to this www.cyberplan.eu, you will not find anything because this site is down for good. So there is no possibility to access to Millipede anymore. I have the latest version, which, by the way, is from 2014, if I'm not wrong, available on my cloud drive. So if you need it, just please send me a message and I will share the link with you. But anyway, it still works. Besides that message, it still works. So the mesh that I want to use is this one. There is also this, well, awful wiring in Millipede. I don't like it, but nevertheless, this is how it works. And now you must define the material and thickness. Okay, so what I'm going to do, I'm going into stock, grab a material. By default, this is set to steel. Well, I'm not interested actually in the material. We could change it to concrete or whatever you want, but nevertheless, this is the material that we want to use. We can change it at any time. And the thickness. Yeah, now the thickness is in meters. So Millipede is set to work in meters. So even if we are considering now this file is in millimeters, remember that we have this kind of object. So probably it makes more sense if this was meters than millimeters. Fortunately, this Millipede plugin doesn't care about the actual Rhino unit. It only cares about the values. So the important thing is that it set thickness properly in terms of values. So if I want this shell to have a thickness of, I don't know, something between 50 centimeters, for example, it's 0.5 meters. Okay. And then the orange balloon disappears, so it means that this thing is working properly right now. And we have the FE mesh. And we can also define the area load, and we can define the normal area load, which is different because well, normal means perpendicular to the surface. So if I consider an area load, I will have the load always oriented vertically, no matter what's the orientation of the mesh. But if I consider a normal area load, the load will be applied perpendicularly to the mesh. Okay. In this case, I'm not going to use the normal area load. I'm using the area load. So per each square meters, you see, I want to apply something like 100 newtons, something like that. It asks for a vector. Sorry, that's why there is this red balloon right now. So you see the vector icon. So I must provide a z vector with a negative value, so minus x, and then plug this 100. So I have minus 100 newtons applied for each square meters of this thing. And so I have set the FE element, the mesh, and also the actual vertical load for this object. We also need to define the FE point support. Okay, so I want this object to be anchored with correspondence to these points. We already have those points. Actually, we calculated twice because we also use the mesh corner after the simulation. We can also use this one. So I want these points here to become a support. And I go in stock and select support type. So this is going to be the support type. And the support type is actually set to true, 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 true. Everything is true. So 6 degrees of freedom, 3 translation, and 3 rotation, they are all set to true. So this is basically a fixed support, as you can see from the symbol. Okay, this is what I want. Then what I need is to create the model. So I will grab this FEA system here. It only asks for model components. We only have this mesh and this support. This is all we need for creating this FEA system. And then there is the solver. The solver asked for the FE model, and actually he already did the calculation. You see, and you don't see anything initially, but you will see that FE model is actually Sat Rhino R stat system, and then here you have the calculated model. Okay. Now, if you want to visualize this thing, there are some visualization components here. Mesh visualization, for example. So let's take the FE model and show this mesh. Now, this is not so interesting because we are seeing the same mesh as before, but this mesh visualization has some option. If you right-click, you are not seeing anything but the mesh itself. But if you want to see, for example, the principal stresses, then you switch to this and you see that the mesh is colored according to the principal stresses acting on this object. Okay. You want to analyze deflection? This is, for example, the deflection of this object in color scale. It means that the largest deflection happens in the red areas. And you see that, of course, this is not a surprise, but remember that we applied the smooth goal here. And the smooth goal was mainly working in this area, just smoothing up this part here. So we lost the catenary function here. We lost the compression structure, which is still available in this area. So that's where you have less deflection. And here you have more deflection because of the absence of this compression structure in this spot here. Okay, so it's not so surprising. Okay. And you can visualize whatever type of force or stress going on inside this object. Okay, and as you have mesh visualization, you also have here, for example, stress lines. So if I hide the mesh visualization and grab the FE model and set it to stress lines, these stress lines is actually asking for points. Okay, so we need points spreading all over the mesh in order to obtain these stress lines. So if I take, for example, some populate geometry, the geometry that I want to populate is the actual original mesh, something like this. I get this random pattern of points on top of this mesh. And I want the stress line to start from those points. So this is the stress pattern inside, well, applied on top of this mesh. These are the stress lines that we were looking for. Okay, so if we use these lines instead of some random connection lines that we created with a non-incestuous network, then we will have the fibers flowing along the stress lines of our object. Now, in this case, I have too many stress lines. Okay, they are divided into two sets, the principal stresses, actually. So if you take a curved container, you can separately see the stress line flowing in one direction and the stress line in the opposite direction. So you can concentrate on both of them at the same time, or on just one of them at the same time, at one time. So for example, let's say that we want to consider these stress lines here. We can decrease the amount of points in the populate geometry, so we will have less stress lines. Okay, so let's say that this is enough for us for creating the fiber system. It doesn't matter. Well, yes, it matters, but it doesn't bother me if we have very close lines, because in the end, these areas here require more structural resistance. Okay, so I wouldn't pay too much attention to this. Of course, you can create a more even separation between these lines. Instead of working with populate geometry, you can simply distribute points in a more regular way by finding a simple way, like, I don't know, drawing a line and dividing it into parts with a constant separation and so on. But I don't bother with this because it's functional to the fiber system. Is it possible to use line from zebra? Zebra, you mean the zebra analysis for curvature? No. That's only a visual analysis for curvature purposes. Also, curvature has nothing to do with structural function or performance. Okay, so it's just some geometric analysis. While these lines here are actually flowing along this principal stress direction. So these are good for creating performant fibers. So basically, the only thing that we need to know once we have these lines here, for example, is to, well, use them as our wanted path. Well, actually not as wanted path, because wanted path is always going to be this hairy thing here in the end, but we are going to use them as the connection. Why, instead of using this connection line here, now we have a more relevant set of curves, which are the stress lines. And so we can go back to our shortest walk algorithm. And instead of feeding it with this kind of fancy curves that we were using, we are going to feed it with these stress lines. These are polyline curves. Okay. You could also eventually, if you want, you can rebuild them before dividing them, but it's not so necessary, because in the end, you are always coming up with some hairs. So it's irrelevant to do this. But if I do this, it's going to calculate a little more, because these are more lines than before. But in the end, we should have some path, you see, that flow along these stress lines. See? The trick now would be, let me also deactivate the, let me take the last step, which is the rebuild that we have here. And I want to turn off, like, Control E, or deactivate the curve to volume, because this can be time consuming. Okay. So I want to concentrate on these results. How do we, well, optimize this result in terms of how do we obtain a less uniform or covering pattern, okay, in order to identify in a clearer way the stress lines. They are visible, more or less. You see that there is more concentration along this line, somewhere around here, somewhere around here. So if we go back and take the stress lines, we can recognize that actually the fibers are following this path here. But the problem is that we have fibers also very far from these stress lines. What can we do in order to change this? Well, actually, the distance depends mainly on the radius that we give to this point cloud, and also on the scale factor of this scaling that we gave to the hairs. Okay, so our scaled lines reach distances which are very far from the actual stress lines. So first of all, let's not scale these. So let's reduce their length. So now you see that we are avoiding filling all the regions with fibers. Okay, so fibers are more concentrated along the stress line. And if you want even more concentrated fiber systems, then you can decrease the radius here. So from 460 to 2, for example. And you see that we are concentrating more around the stress lines. And also you can eventually decrease the amount of random points along this stress line, but this is not so efficient if you want to reduce the amplitude or the width of these fiber systems. Okay, and so finally we came up with this kind of result. Um, of course, everything depends on the pattern that we create. So take a look at this. Well, of course, I'm going to save this. I didn't save it already, so I was at high risk of losing everything. So let's save it immediately. So yeah, here it is. Okay, let's go back to Blender. Okay, now we are using this kind of structure here, well, of let's say truss system. But remember that everything in Blender is non-destructive. Well, at least the workflow that we are using is non-destructive. So we can change this as many times as we want by changing the module. So for example, let's say I want to use a different module instead of this one. And I want to go into edit mode for this and keep these things here separated. So I erase with X these edges. So I have separated chunks here. Now, this is an oriented model, right? You can recognize it because this flows in one direction differently than it flows in the other direction. Okay? So it would generate a striped pattern on top of this surface. And everything will work fine because we already have a regular set of loops along this mesh. So if I go here and go into tessellate settings and refresh, now I have this thing here. And I also want the rotation to be applied by active UV. So you see that now we have these chains basically flowing along this mesh. And we can also invert the direction by shifting the rotation. Okay, so now I have a truss system made up of chains of connections along the loop lines. This doesn't change anything because in the end, in Grasshopper, we will be following the stress lines. So the fibers will always come up according to the stress lines. So this truss system here is affecting more the aesthetic of our geometry, of our fiber system, not the function. So if I go back here to export, you see that everything is still the same. I re-export mesh data. This is overwriting the old version. So I go back in Grasshopper. The import happened here. So if I set this to false and true again, I'm now importing the new version of the truss system. And you see that things have changed slightly because now we have chains. And the fact that we have chains, it means that there is no communication between one structure, well, one truss line and the other truss line. So even if we have, I don't know, something like starting point here and we create the hair and scale it up so it reaches this length here, there is no way for this fiber to leave this line because this is physically separated from the next and the next and the next and the next. So there can be no fiber that flows in this direction. Okay, so you can change the condition in your system according to the truss structure that you want to use. How can we eventually create more fibers in this case? The only thing that we can do in this case is increase the amount of points in the populate geometry, because we hope that in that case we will have more stress lines, you know, that will flow also in different regions in order to create more fibers. So if I go back here and say I want, for example, double the amount of points, I will also get double the amount. Well, not necessarily double the amount of fibers, but more or less, I'm doubling the amount of fibers. If I want more, I increase the count. Because in this case, there is basically no possibility of tweaking these parameters here or the scale, because our structure is simply flowing like this in separate rails. Nevertheless, this is something very interesting, because if we manage to obtain, I don't know, let's change the range of this populate geometry to a very high value. So let's give this something like 500 points. We start to obtain fibers that follow the actual truss system. Let's see, let's give it time to calculate this. Maybe I exaggerated a little, but it's nice to see the final result with a huge amount of geometry. Remember that this fiber system makes more sense when you have lot of geometry. So we start seeing this kind of irregular fibers flowing along these lines. And they concentrate more where you have stress lines. Okay, so the principle is always the same. The higher the stress of the surface, the higher the probability of having fibers in that area. Okay, so this is still performance-driven fibers, but I think it's less functional in this case. Okay, so when you create your underlying truss system, try to avoid disconnected parts, because else in that case you will limit the possibility for the fibers to spread in any direction. Okay. So this is something that you simply do by tweaking the module that you are going to tessellate on the base mesh. We can also create a simpler system, and it's nice to see how this module affect the aesthetic of our fibers. It doesn't necessarily have to be something like this simple. You can work with more complex shapes, but remember that if you add many edges to this module, you will have thousands and thousands and thousands of edges coming out from the export. And then eventually you will have very heavy calculation going on in Grasshopper from the shortest walk algorithm. So pay attention to this eventually. So say I don't want a square anymore. What I want, for example, is I go into edit mode, select the vertices, I take these two here, create the edge, and then Control R, like loop cut, and create a vertex here at the center. And then I have two separate edges, 1 and 2, and I also can obtain this and this. So I am connecting this diagonally at the center. And I can also get rid, for example, of these two edges here. So X edges. So I have a different model, which is actually intersecting at the center and at the corner. Okay. So I can update this. So refresh, and we have an interconnected pattern of lines inside all along this mesh. So this is actually set to true and remains true. I don't remember honestly if it updates automatically the moment these txt files change. Let's double check. Let's concentrate on this. It will be very easy to understand, because the mesh will be able, the fibers will be able to shift from one line to another line. So it's going to be very easy to understand if it happens in real time. So let's re-export this and let's switch to Grasshopper. And you see that no, nothing happens. So you have to switch this to false and true again. And now eventually we will have to tweak back the amount of populated geometry points, because it's going to be quite a dense set of fibers because of the amount of stress lines that we are calculating from millipede. Let's see, this is going to take some time. I think we should, let's say, decrease once again the amount of points down to something like 20 or 30, something like that. But you see that now the pattern is totally different. You see this kind of diagonals or you know, yeah, basically diagonal lines coming out instead of the actual initial fibers. And we can go here, and instead of 500, let's go back to, I don't know, 70, in order to have, well, much less lines. And you see that this is actually the result that we are obtaining. And in this case, this rebuild, um, the rebuild that we should do, because here we have the actual truss, and here we have this shortest walk, clean, and rebuild. Now this is quite important because this is a huge amount of control points. So if we decrease this, we can also get some kind of more organic pattern for this surface. This doesn't change the fact that there is more density corresponding to the stress lines of the surface. Okay, and as for the result, remember we have a curve to volume, and we also have a mesh actually. So if I turn on the preview of this, this is what we are getting. It's like with Cocoon, we get a volume that flows seamlessly from one fiber to the other. So it's just one single volume in this case. I can bake it and have it available here in Rhino. And we can also take a look at this from a rendered point of view, like this. Okay, so something like this. Of course, in this case, for example, it would be also useful to have the preview of the original mesh, because maybe this structural system will hold the underlying mesh. Okay, so this is the reason why we are creating this kind of systems. But another thing that's interesting, and this is the last thing that we are going to do, maybe sorry for this, especially Sagar, which is quite late where you are, but we are going to finish some, I think 10 minutes later. I prefer to, let's say, complete this workflow. You see that we have these curves, right? So when we work with curve to volume, we are giving the same thickness to the whole, okay, we are giving the same thickness to the whole path of the curve, okay? But one thing that could be interesting is this. We know that we have a stress line, okay? And we know that we have an underlying structure of lines, which is the one that we created in Blender, okay? And so the fiber system starts from somewhere from this stress line. Then there are some hairs flowing in random directions, actually. And the shortest walk actually does something like this, right? So it finds the shortest walk in order to get to the point. Now, if I give this path here a unique thickness, I will have the same thickness at each level of this fiber. But the stressed part of the surface is more sticking to the stress lines. So I need more resistance close to the stress line and less resistance far from the stress line, right? So what if I give these fibers a variable thickness, which is thicker when they are close to the stress line and thinner when they move away from the stress line? Okay, so this is my goal actually. So how can we do this? We cannot work with the curve to volume because this gives a unique thickness to the whole fiber. Okay, but if I take the rebuild curve and start dividing this curve, now there is one question here, which is this one. This curve have a different length. Okay, and as they have a different length, if I divide them all with 10 points, for example, or in 10 parts, I will have a variable density of points, because if the line is shorter, the points, the division point will be closer to each other. If the line is larger, then the points will have more separation. So I do prefer to use another division method, which is the divide length, which is this one. So I can decide what's the separation between two consequent points, rather than the amount of points that I want. Remember that we are working with some units. So for example, I do recommend in this case, we start with 1. And this creates a more uniform set of points because the separation is constant along the fibers. Okay. Now we have these points. These points are divided by fiber. So when I have, for example, first branch, 2 points, This is because the first fiber measures more or less 1, which is the length of the separation between two consequent points. But then there is also the last branch, which says n equal 8. This is probably a long fiber. Okay. So what I want to do, I want to determine the convert these points into volume, giving a thickness that depends from their distance with respect to the stress lines. So we have the points here. Instead of using curve to volume, I'm going into Dendro and use the points to volume. Okay, so I want to convert these points into volume, and this actually must be a list. We can also flatten this list of points. It doesn't matter actually if they belong to a curve or to another, because we only want their radius to depend on the distance from the stress lines. Point radius. Let's make point radius dependent from the distance exactly. And the way we calculate the distance between a point and a curve, the stress lines are actually coming from millipede. They are here. I'm going to copy paste this container and bring these curves right where I need them. So here are the stress lines. Okay. So these two things are the things that we need. I'm also going to hide the fibers for now. So we only have stress lines and the division point. If we use the curve closest point, we can calculate the distance between point and curve. This is a list of points. This is a list of curves, 70 curves. I need to calculate the distance between one point and each of the curves in order to understand if these points are far or close to any of these curves. So I need to graft the curves. Okay, so I'm calculating the distance between the point cloud and each of the stress line independently. Okay. Despite the projection of these points that we get along the lines, the stress line, which is not relevant for us, what I'm interested into are the distance value. Okay, so you see that we get 12,576 distance values in 70 branches. So these are the 12,000 distances of each point, 12,000 points, with respect to each one of the 70 stress line individually. So basically, in one branch, I have the distance of one point with respect to one stress line. On the other branch, I have the distance between the same point and another stress line. Okay, so I have the distances subdivided by stress line. What I want is the distances to be subdivided by points. I want to know if one point is close enough to any of the stress lines. So I need to basically flip this matrix of distances. I now have 70 distances per each branch, and I have 12,500 branches. So the branch represents one single point, and 70 is the 70 distances that that point has with respect to each of the stress lines. So in order to understand if this point is close to a stress line, what I can do, I can mass addition these numbers here. So the 70 distances are now being added, and we are coming up with one single value. Okay. We can also take a look at this. Okay, so if this value is small or large or whatever, it means that this point is more or less close to a stress line. I can, for example, remap these distances here. They are just one value per point, so I can also flatten this. And so I get a list of the addition of distances. I can use a bounds for determining the source domain of these distances, and I'm actually remapping them between 0 and 1. Okay, so I will have values between 0 and 1 corresponding to the global distance between one point and all the stress lines. Okay, so basically what I need to do now, I have 12,576 point, and I have 12,576 values here. If I connect these values to the radius, okay, and I use, for example, the same volume settings that I was using, I now start to have this thing. You see that the volume is getting thicker in the areas where we have basically points that are farther from, or an average, on average, farther than from the stress lines. This is not exactly correct, because you see that we have basically more volume here in the peripheral areas, because the main density of stress line lies here. So it means that something that we did here was not properly correct. Eventually, I think that this was the thing. I cannot simply make a mass addition, because else I'm simply separating the farther points from the closest points in general. So I should keep this separated as a workflow. Eventually, if I don't flatten this, maybe I will get a better result. So let's see if I can do this in another way. Probably I would better separate this point by distance, actually. I could, for example, take this point cloud and put them in relation with the stress lines somehow. I already did this here by calculating the distance, but it's not enough. So I'm getting one single cloud of distances, or points and distances. So eventually here, we could also maintain these points separated per fiber. And eventually this also could help. Let's double check. I'm going to deactivate this, Control E. Let's eliminate this flatten here. So we are still considering the points belonging to each fiber. I'm projecting those points onto these curves. Problem is, here we must change the data tree structure, probably. 1746. No, it's still working. It's still working. Flip matrix is actually working. We have 1746 and this, but I think this is not exactly working, because flip matrix only work when you have a rectangular matrix of data. And as we have a variable amount of numbers inside these branches, you see n equal 2, 2, 2, 1, 3, 3. So the flip matrix eventually is working in a weird way. This is giving us an error. Not all input data types are supported, probably because here we missed something. Let's double check quickly. They should all be number. So if everything is correct, oh yeah, there are some nulls, you see? I saw them, yeah, here they are. Okay, so this is the point. And if you want to avoid this red flag here, it's just another clean tree. So remove null, and now we pass this to this, and everything goes back to normal. So it's calculating the sum, the addition. We avoid flattening this, because we want to keep this like it was. And maybe now we should have something divided by fibers. We have 22 branches, and here we have 1746. That's because we flipped the matrix. Okay, so 1747, 1746, because of this clean tree. This is something that is not going to work exactly good, but if I reflip the matrix here, I'm going back to 1000. Oh, this is one single value. Sorry, I must flip this before the mass addition. Yeah, something like this eventually. And we also get null items. No, this thing is not going to work like this. Sorry, but in order for you, I think we are not able to complete this like I was hoping. But what I will do, I will send you an updated script with the right solution, in order to have the thickness of the fiber depending on the distance from the stress line. But what I can do in the meanwhile is a simplified version of this. So I'm going to flatten this population of points. Let's wait for this calculation to end. Yeah, here it is. And instead of creating a multi-attractor system, because this is what we are doing here, we are considering all the stress line as attractor. This is the thing that is complicated things a little. What I'm going to do, and I repeat, I'm going to send you the final definition in the email, or I will share it together with the video once it's online. What I want to do, I want to determine the radius of these points according to the distance from something. Okay. So, for example, this is very simple. I'm going to do with a simple attractor, something like a point, like set one point here at the very center of the mesh, and then I calculate the distance. This is exactly the same process, okay, but without the complication deriving from the data tree and multi-attractor system. Okay, so it's absolutely the same. And so I can remap this number from their original bounds. Sorry, what I say, bounds, which is this one, to another value, which is the target. The target is by default 0 to 1. Now remember that Dendro needs these particular things. So if you decide a particular size, then the voxel size must be that value divided by 1.5. Okay, so we also have to adjust the settings for Dendro. And what I want is that this mapped value here, which I'm going to use as radiuses, I want them to basically also adapt to this condition. For now, I'm only plugging these volume settings here. So now, if I hide these points, you see what's the meaning of this situation here. If I take this point, which is the attractor, and I move it, I am basically defining the thickness or basically the size, the thickness of this structure according to the distance from the attractor point. You see? Of course, I'm using a very let's say problematic values, because actually I'm giving as point radius values between 0 and 1. Okay, but we know that if we want to get some result, we must use this value actually. So if I create a domain, construct a domain that instead of going from 0 to 1 goes from this value 0.25 to 1, then I will have 0.25 close to the attractor point, which is here, and 1 when I'm far from the attractor point. So you see that now I always get some thickness along these fibers. Okay, and this separation here, these dots here, depends on the fact that the length is set to 1. So I need closer points along these lines in order to have a more continuous aspect for these fibers. So you see that the smaller this value, the more point I have along the lines, and the more they join together, they blend together according to the thickness that they are receiving from the remap numbers. Okay. So of course, if you imagine this, instead of working with an attractor point, if we could use, like I will, and I will share with you, all of this line as attractor, we will be having thicker volumes stick to the stress line, and thinner volumes far from the stress lines. And so we will have finally a fiber system which is more resistant along the stress line and less along the areas which are not subject to a big amount of stress. Okay, I hope at least it's clear what I was trying to do. Is it okay? Are you okay with this? Yes. Okay, Sagar. Atish, are you okay? Yes. Well, that's pretty it actually, because we covered all the topics, and we could also manage to obtain the stress line via millipede instead of Karamba 3D. Sorry for that, but I didn't get the workshop license. But anyway, this is more than enough. Eventually, we missed some rebuilding of this polyline, but I told you it's not so necessary. One last consideration. Even if we are following stress lines, remember that this doesn't mean that this, for example, this part where you have this stress line deserve the same importance as this part here, for example, because these stress line are determined by a random population of points. Okay, so eventually you should determine the stress line according to the more stressed portion of this mesh. So there is something more that you should do with millipede in order to understand what are the more stressed areas, which is something that that depends also on this colored representation, where you calculate, for example, the I don't know, the principal stresses and so on. Then in that case, you might need more stiffness in those areas. Another parameter that you might use is the deflection, because the more deflection you get, the more resistance you need for the structure to bear that particular part. Okay, so also this could be another important value. Um, so bending moments, you can analyze these things under many different, let's say, point of views. So von Mises stress also, which is also interesting. So bending moment, principal stress, which probably is the more important value in this case. So you know where the surface or the mesh is getting um, the highest values for the highest amount of stress. So this could be a good way of determining the um, thickness of your fibers, okay? But also deflection, remember. The body tends to deform more where it has less resistance, basically, okay? But yep, that's pretty it. So that was my last consideration. Um, just double check if we can quickly what result. I think it was a good way of determining this kind of thing, because this quad result is actually determining or creating these principal stress frames, which are oriented, aligned according to the principal stress orientation for each point. But what is interesting here is these, which are the values of principal stress 1 and principal stress 2. So you could concentrate, for example, on the values that you get from here in order to derive the stress lines. You can also use, for example, the output from these quad results. You see you have principal stress frames, 600. They are quite a lot. So let me turn off everything that comes after this. Okay, I want to just concentrate on the stress line. Now the stress line is just 70, but if I use all the principal stress frames as points, I get a huge amount of stress lines. And the thing is that each of these stress frames, they are 600. You also have associated 600 values for the principal stress 1 and principal stress 2. So you can concentrate on specific stress values. So for example, you could understand, let's see what is the min max of this. This is another heteroptera component, by the way. So for example, let's concentrate on stress 1. These are the lines that we were considering, okay? So it's this. And now I know that this is actually ranging, let me see, between 1.64 multiplied by 10 at the 7th and 1.25 more or less multiplied by 10 at the 6th. So this is the range for the principal stress. And I want to concentrate only on these areas where the stress is maximum or it's relevant, okay? Now, what I need to do actually, this is the minimum stress and principal stress and the maximum principal stress. But you see that we are not talking about, oh, this is small and this is big. They are both big, okay? So the fact that this is minus 1.64 doesn't matter because it is multiplied by 10 at the 7th. So it's a big value, okay? So if you want, you can also create here an absolute component. where you take all these stresses and just concentrate on the absolute value. Okay. Sorry, these ones here. So I want the absolute values. Okay. So now we know if we perform the same calculation but with this result, we get the actual variation in terms of absolute value of the stress. Okay. Now, if we do this, we understand that this is the smaller stress and this is the higher stress, no matter if it is minus or plus. And so if I want to understand what stress is worth considering, I can, for example, concentrate on values that are larger than, for example, like this. Values that are larger than, I don't know, the average values between this one, just to have a reference. Okay, so I take the average, take this. This is going to be the arithmetic mean. And I want to understand which stress is larger than this average value. I will get some true false here. Okay. And then I can also call pattern what? All the principal stress frames according to this pattern here. And now we get only 16 frames. Maybe the average is is not properly correct because we only get these. Of course, the major principal stress is located close to the base. This is something that was easy to foresee. But if we use only these frames here, now we will have only the stress lines, sorry, the stress lines that are more relevant. Okay, so these are more relevant than the other one. But nevertheless, we have 31 to, what value is this? Well, it's difficult to, we need to multiply this by 7 times by 10, so 1, 2, 3, 4, plus 3 zeros. So it's 16 million, more or less. Okay. So if I take a slider like 16, 1, 2, 3, 1, 2, 3, I could also define this slider. Of course, I can decrease this and get more stress lines. Okay. So when I increase this, I'm only concentrating on the really important stress lines along this structure. Okay. So I'm excluding useless stress lines. And if I reactivate this, and now I only have 16 polylines, but nevertheless, you will see that the structure is going to come up a little lighter than the first one, you see, but the meaning is absolutely the same. Don't pay attention, of course, to this attractor point, because this is giving us some fake thickness, which is not the actual thickness that we need for the fibers. Okay, but nevertheless, the process is good.